Hello everyone, I'm Alicia and I'm a PhD student at UC Berkeley. Today I'll present our work on robustness analysis of deep learning via implicit models. In this paper, we analyze deep learning models through the lens of implicit framework and introduce the sensitivity matrix, an intuitive analysis tool to understand the input-output relationship in neural network. First, we introduce the implicit models and its prediction rules. In contrast to most current neural network architectures, implicit prediction rules are not obtained via a recursive procedure through multiple layers. Instead, they're based on solving a fixed point equation in a single state vector x. Given an input vector u, the implicit prediction rules is given in this two equation. Phi here is a nonlinear activation map, and matrices ABCD contains model parameters. The model above provides the state vector x only implicitly, and in general cannot be solved in closed form. The equilibrium equation is not necessarily well-posed, meaning that it may not admit a unique solution or even any solution. We provide an example in the scalar case here. On the left, the equation has two or no solution depending on the sign of b, and on the right, the solution is unique for every b. Interestingly, a large number of deep neural networks can be modeled as implicit models. And most of these models satisfy the well-posedness property, for example, strictly upper triangular matrices. Here we show two example neural network architectures. On the left is a fully connected feed-forward neural network with L layers, and on the right is the model matrix A for ResNet20 when formulated using implicit framework. We see that both of them are strictly upper triangular. Now we can analyze the robustness property of a given neural network model via its implicit model representation. Assume that the input vector is uncertain and belongs to a given uncertainty set. We also assume that the activation is component-wise non-expansive and that well-posedness is satisfied. We're interested in bounding the variation of the state vector x given the uncertainty of the input. If we write out using the implicit representation, we can show a component-wise bound for the variation of the state vector x. And in the same way, we can also bound the effect of input noise on the output vector y. Precisely, we can derive the matrix S and get a closed form expression. The metric S is the sensitivity matrix of the implicit model. The implicit model formulation opens up the possibility for us to bound the distortion of the state vector x and the output against the unknown but bounded input noise. Particularly, the sensitivity matrix provides a way to visualize the input-output properties of a given deep neural network model. We show the sensitivity values for a particular class on MNIST and CFAR10 dataset. The sensitivity values are obtained from the implicit representation of the feed-forward network and ResNet20. On the left is the sensitivity values of the image digit 0 for MNIST, and on the right is the sensitivity values of the image airplane in CFAR10. Brighter colors here correspond to features with a significant impact on the output when perturbed. As a result, the sensitivity matrix can be used to generate adversarial attacks, especially sparse attacks. Here we show examples from MNIST. On the left are dense attacks with small perturbation, so we can see that the gray pixels are the perturbation, and on the right are sparse attacks, and we mark the perturbed pixels as red for higher visibility. This is another sparse attack example on CFAR10. The left ones, so these two, are clean images. The middle ones are perturbed images with sparse attack. And on the right, we mark the perturbed pixel in red for higher visibility. And we can see that the sensitivity matrix actually provides a very easy way to generate these sparse attacks. So in conclusion, in this work, we introduce the implicit model and the theoretical properties of well-posedness, and observe that the implicit framework includes most current neural network architectures as special cases. Therefore, implicit models are a much wider class, which opens up the possibility for a formal analysis of the robustness for any given neural network. And finally, we showed that the sensitivity matrix provides an easy and intuitive measurements that can be used to systematically highlight potential vulnerable input features and generate successful adversarial attacks. We believe that the theoretical ideas developed in this work will be useful building blocks for future research, especially for designing robust training algorithms and choices of regularization penalties that can be used to train a robust deep model.